this video, we'll start a third case study with the debit card data. To begin with, in this case, we'll read the ATM data with the following attributes. Variable y equal to 1 if it is a debit card ATM card holder, 0 otherwise. Account balance variable x2, which is average account balances in hundreds. Number of ATM transactions, that is number of ATM transactions in a month. No other bank service. So if no other bank service is received, then 1, 0 otherwise. Receives interest. If interest is received on the account, then 1, 0 otherwise. City banking, city code where banking is done. We'll read the data in R and then we'll conduct the following analysis. First, we'll run a simple LPM linear probability model, which will examine the relationship between y as the dependent variable and x2, x3, x5 as the independent variables. We'll examine, summarize, and interpret the results with and without robust standard errors. We'll examine the fitted probability values. Then we'll estimate a non-linear logic probit model. Subsequently, we'll compute the marginal effects as we have understood. We'll compute pseudo R square, also called McFadden's R square. Then we'll conduct the likelihood ratio test and examine the fitted values. We'll compare the goodness of fit measures for logic probit models. Lastly, we'll assume a threshold of 0.5 and compute the percent of observations accurately classified as and which is a count R square for both the models. In this third case study, let's start with the part 3 of the case. Part 3, ATM data case study. We'll start the case by reading the ATM data. All we need to do is run this command ATM. For reference, we'll copy paste this command. So I just copy paste this. Now, as a practice, we'll have a glimpse of this data. Although we know what are these data, we have already discussed them. So account balance, number of ATM transactions, no other bank service, number of other bank services, debit card, whether owned or not, receives interest, city banking, and so on. Let us start by running the simple linear LPM kind of model. So when we run the LPM model, what we'll do is we'll name it model underscore LPM, and we need LM modeling. We have this debit card variable, and we'll regress it on account balance plus number of ATM transactions. Then another important variable is whether it receives interest, and data is ATM. So this is our linear probability model. We'll run this model. Let us summarize this model. So the simple approach is either we can summarize it like this, and we can also run the QF test approach with robust standard errors. That is also there. Model underscore LPM with VCOV equal to. So both the approaches we can use, and let's see what are the significant coefficients. So when we run the LPM approach, you can see receives interest, it is significant. Here also account balance is significant, receives interest, that is also significant with the same sign. So we can infer two things here. First and foremost, if account balances are positive, then there is a higher probability to own the ATM debit card. And if they are receiving if they are receiving the interest on their savings account, then the tendency to own debit card is lower. So now let us examine the fitted values. So fitted probability values. How do I examine that? Simple. I'll use this model underscore LPM dollar fitted value. So because this is linear probability model, effectively these are fitted probabilities, and there are many numbers. So what we'll do is we'll summarize them. So I can summarize them. That is one way to do it. This will give us some idea. So values range from 0.12 to 0.76. So this is okay. They are well within 0 to 1 range. So that is not a challenge. Let us apply logit and probit models now. So let's start with the logit probit approaches. So first we'll use model underscore logit. The way to do it is use GLM. Now I'm going to use the same set of variables, so I'll just copy paste them. Already we have seen that some variables are not so useful, but still we'll test them. So data is ATM, family is equal to binomial. Family equal to binomial. So this is our logit model. Similarly, I'll calculate probit model. Let's call it probit. Now here the way to do it is family equal to binomial link equal to probit. So now we have both the models ready with us. Let us summarize them. So if I apply the summary of model, we'll compare them as well. Model underscore logit. So this is your output you get in as per the logit. This is the model you get. Again, receives interest significant, account balance is significant. Let's see if probit has a very different kind of result. So let's apply probit. So when I run probit, I get a coefficient of, although this does not have a bigger sort of implication, but minus 0.83, it has minus 1.35 with logit, and this has 0.0012. So not very similar, but pointing toward the same direction. Both the coefficients, they are significant and pointing toward the same direction. Let us look at the marginal effects. So marginal effects, let's apply marginal effects. First on, okay, so these are, oh, I want marginal effects as mean, so rather margins. So you can see the margins. These were like entire for all the observations. So rather we'll look at marginal effect means. So you get these marginal effects. These are generally marginal effects at averages. Similarly, I can compute marginal effect of probit. They are very, in fact, very close. So we are slightly more confident about our results. If you want to compute marginal effects for all the observations, you can apply this marginal effects. And these are marginal effects at averages. So let us compute the mar margins. These basically they give us the marginal effects. So I can compute margins here, model logit. Similarly, I can compute model probit. So their marginal effects are pretty similar if you compare the values for both logit and probit. So you can print your margins at averages. This will give you the margins at averages. Now, if you want, these are average marginal effects. So suppose you want the entire range of it, you can apply this margin summary. So you can apply this summary. For example, for logit model, let's apply the summary. You can see the lower and upper limit, the Z value, the P value, confidence interval and everything. So you can see account balance and received interest are significant. Similarly, you can produce the margin summary for probit model. So you can get the margin summary for probit model as well. Lastly, if you want goodness of fit measure in the form of pseudo R square, then you can produce your model logit. If you run it, you can see your log likelihood and pseudo R square here. Similarly, you can produce your, with this PR square, you can produce your probit also. Look at it, you can produce almost similar values we are getting. So that means logit and probit models are giving us very similar results. Now let us interpret these average marginal effects. So first and foremost, looking at this number 0.03% of account balance, it seems that customers with higher balances on average, for each unit increase in account balances, there is a 0.03% higher probability of owning the debit card. Vice versa, whatever interest is being received for per percentage point, for each percentage point increase in interest rates, there is a 30% chance the ownership of debit card declines by 30%. So if there's 1 percentage point increase in the interest rate, then the probability to own the debit card decreases by 30%. One can also interpret this no ATM transactions. For example, on average, depending upon number of transactions, so for each unit increase in for each increase in transaction, on average, each increase in transaction, the probability of owning the ATM declines by 2.9%. But this result is not significant. Finally, in the last part, we'll compute another measure. We'll assume a threshold of 0.5, and we'll see the compute the count R square measure. That means what percent of observations are correctly classified with a threshold of 0.5. Now, this requires first using the threshold, we need to classify the values, predicted values into ones and zeros. So first, if else, we need to use the model fitted values. So model dollar fitted values. Now, please recall these are fitted probability. So they will lie between 0 and 1. So let's start with model logit values. So let's start with the logit values, and fitted value should lie between 0 to 1. Let's classify those greater than 0.5 as 1, others as 0. So let's call it predicted by logit. So these are predicted values from logit. Similarly, we'll use the predicted values from probit. So model underscore probit. So they are here. Now, how do we know the correct values from logit probit? So what we'll do is, let's call them correct from logit. These are equal to sum of actual values. So how do we get actual values? So actual values from the model are provided here, debit card. So the data name is ATM. So ATM dollar debit card, and if it is equal to predicted by logit. So all the truths will be summed up and it will be assigned. So these are the correctly predicted values as per the logit model, and similarly I can compute the correctly predicted values by the probit model. So predicted probit. Oh, now all we need to do is compute count R square. So let's call it count R square underscore logit, which is equal to correct by logit divided by the actual data. So the actual data is our ATM data. So this should be the right dimension. So this is count R square for logit, which works out to 58%. Let's do it for probit. Probit. So here I need to provide for probit. Probit 58. Oh, so we are, it seems that whether it is logit or probit, correct probit, how many values we are getting? 35. So almost identical results we are getting because the model results very similar. So we are getting the identical results. So in this example, we examined the ATM ownership data and we found that logit and probit models were giving very similar results. In this video, we'll introduce fourth case study, which is grade point average data case. In case 4, we'll read the GPA data with the following attributes. The data has grade variable y, which is 1 if the final grade is A, otherwise 0, which may include B and C grades. Then we have GPA grade point average data, which is a numerical grade point obtained previously. Then we have test of undergraduate course in economics, TUCU data, which is score in the economics entrance test. Then we have personalized system of instructions, which is PSI. The variable takes a value of 1 if the candidate was exposed to the new teaching method, 0 otherwise. Then we have letter grades, grades A, B, and C, We'll start by reading the data in R and then conduct the following analysis. First, we'll run the logit and probit nonlinear models examining the relationship between variable y, which as defined earlier, with as dependent variable, with GPA, TUC, and PSI as independent variables. We'll summarize and interpret the results. Next, we'll also compute the marginal effect pseudo R square, also called McFadden's R square, and likelihood ratio, and examine the fitted values as well. We'll compare these goodness of fit measures for logit probit models, as we discussed the pseudo R square and so on. Lastly, we'll assume a threshold of 0.5. We'll compute the percentage of observations accurately classified through count R square for both the models, logit and probit. With this, we'll conclude the case. Let us start with the GPA case, which is part 4, case study number 4, GPA data case. First and foremost, let us load the data. So this is the data file GPA. I'll copy paste this data file for reference. Now to begin with, let's have a glimpse of this data file. So let us see what are the variables inside. So we have the GPA data here. Then you have TUC data file. You have PSI, grades, letter grades. So we have already discussed these variables. First and foremost, we'll start modeling with the logit and probit approaches. So let us first define the formula that we are going to use. The formula is simple. We are modeling the grade variable as a function of GPA plus TUC plus PSI. So these are our variables. This is the formula that we have specified. Now let's call it model underscore logit. So we'll use this model underscore logit, this as GLM, and inside we'll specify the formula that we are going to use. Next, we'll also specify the data. So we are going to use GPA data, and lastly the family is binomial, binomial. Let us run it. So once I run the model, next I'll use the same scheme. But now I want to run probit, so I need to specify that family equal to binomial and link is probit. So this would be our probit model. So now that we have run the logit and probit models, in the next step we'll try to summarize the results obtained from these models. So first we'll summarize and compare them, both the results. So one is logit results and the other is probit results. So let us interpret the output here. For logit function, we can see GPA variable is significant and PSI is significant. We can see that. Similarly, for probit also GPA is significant and PSI is significant. Now, while we can understand the significance of the variable, it is difficult to interpret directly in terms of the relationship of these variables. All we can say that these are interpretation are true for logit of the model. So for example, let's look at this 2.83 or 2.826. We can say that on average, each grade point increase significantly increases by almost 2.83%. So we can say that if there is because this is log of odds ratio, so we can say percentage increase in odds ratio. So we can say if there is on average 1 unit increase in the GPA, then we can say there is a 2.83% increase in the probability of achieving A as compared to B and C. Similarly, this is PSI 1. So that means corresponding to this, if a student was exposed to the new teaching method. So we can say if the student was exposed to this new teaching method as compared to if a student was not, then the probability or the chances of the odds in favor of getting a grade A increase by 2.37%. The logit, the numbers are slightly different. So for example, here it will say that there is 1.62% increase in the odds in favor of getting A grade if on average GPA increases by 1 unit. Similarly, if the student was exposed to new teaching methods, the percentage of odds increases by 1.42% in favor of getting grade A. Now we need to do a little bit more analysis. We need to examine the marginal effect here. So let's examine the marginal effect. Examine the marginal effects. So for that, we can use this margins. Either you can use this marginal effect, maybe margins command. So model underscore logit. You can summarize that. You can see the average marginal effect. Now these marginal effect can be interpreted in terms of probabilities. Similarly for probit, we can run that. Now they are quite similar, so that eases our job. But we also recollect that GPA and PSI1 were significant. TUC was not very significant. So let's focus on this GPA and PSI1. First and foremost, at average, so we are interpreting this as average effect right now. These are average effects. So we can say that 1 unit increase in grade points on average, 1 unit increase in grade point leads to an increase in probability of 36% for getting A. Similarly, almost similar 35 to 36% probability increase if the student was exposed to new teaching methods. However, if you want more detailed marginal effects, so what you can do is you can run this command for margin summary and you can apply it here to get the average marginal effect, which you already saw, and also get the lower and upper band. Here you can do the same thing for probit. You can get the summary and you can get the lower upper band and their significance. And okay, so here as we can see, if you look at the marginal effects, we do not find TUC also as significant. In fact, we find PSI1 as we discussed and GPA, these two are significant, which we already discussed. So it's consistent. In the next video, we'll examine the goodness of fit measure and conclude the case study. In this video, we'll examine the goodness of fit measures from the model. First, we'll look at the fitted values, that is probabilities, fitted probabilities, and also compare the model performances. So first, let us start with examining the goodness of fit measures. Predominantly, these are two goodness of fit measures that we tend to look at. One is log likelihood and other is pseudo R square. Later on, we'll see something called count R square, which is sort of measure of prediction, how good prediction is. So first, there's a very useful function called PR2 or PR square rather. So here, if I provide model underscore logit, it gives me multiple measures. Our focus will be on likelihood, which is this G2, and McFadden, which is similar to pseudo R square. If you recall the discussion, there was something like pseudo R square equal to 1 minus log likelihood divided by log likelihood for naive model. So this McFadden is for that. But there are other numbers also it is provided. You can type question mark and have a look at in more detail about this function, what exactly it has to offer, what kind of goodness of fit measures it offers. You can look at all of them. In any case, we are focusing more on this G2, which is log likelihood, and McFadden. So we'll compare both for both logit and probit. So we can see McFadden gives us a pseudo R score of 37% in both cases, and likelihood values are similar. That means logit and probit are giving us similar kind of fit. Similarly, if I look at fitted probabilities, let me just summarize the fitted probabilities for logit. They are here, and similarly here examine the fitted probabilities. So they range from 0.024 to 0.945 for logit. Let's see for probit. In fact, quite similar. They start from 0.016 and go up till 0.95. So similar kind of distribution we observe. More importantly, if you want to compare, we would like to see how prediction probability there at different threshold values, how prediction is there. So let's do that for a threshold value of 0.5. So let's define tau is 0.5 as our threshold value. Now, first and foremost, we would like to create this predicted object. So let's call it predicted logit. And that is, so what we need to do is we need to look at the model underscore logit dollar fitted So these are fitted values. If it is greater than 0.5, we assign 1. If it is not, then 0. So these will be your fitted values. We are converting the fitted probabilities into ones and zeros for logit model, and also for probit model we'll do the same. This is first part. Then we would like to compare the accuracy. So correct prediction is correct. So how do I predict the correct? So for that, what we need to do is we need to compare these predicted with actuals. So what is my actual data? The actual data is GPA dollar grade. So this is my actual values. If it is equal to predicted values, then it will be true, and we'll sum this up. So we'll sum it up. So this summation will give us the correct values. Now, if I divide this correct value for logit, if I divide by the total number of values, and the total number of values can be simply the dimension of the data. For example, dim of GPA1. So this would be your count R square. So you can call this as a count R square for logit. And in case of logit, the correct predicted values were 26. The same thing we can do, and the count R square, the measure that we are interested in, count R square for logit, how 81% values were fitted correctly. So comparing the model performance. So same thing we'll do for probit. We would like to compare for probit. I'll just change the name from logit to probit the way I've written the codes, so it is easier. So I'll just run same for probit, and again same number. So which means I guess with probit also I'm getting 26 correct classification, and most likely these would be the same observation. So the same observations would be classified with probit and logit. Generally this happens when your data is symmetrically distributed. There are no extreme skewness like only zeros or ones. If the data is fairly symmetric, then in that case logit and probit tends to give you the same result. And now we have seen the performance. Their performance are quite similar across the board at different parameters we have seen. Coefficients were also quite similar. So with this we conclude the exercise. In the series of our classification case studies, now we'll discuss the fifth case study, which is the smokers data case. In this case 5, we'll read the smoke data. It has the following attributes. It has a smoke variable Y, which is 1 if the person is a smoker, 0 otherwise. Age variable, which is the age of the person. Education, formal education of the person in years. Income of the person. Pricing of cigarette. We'll read the data in R, and then we'll conduct the following analysis. First, we'll run the logit probit nonlinear models to examine the relationship between smoker, which is a dichotomous dependent variable, with age, education, income, and pricing. We'll summarize and interpret the results. Next, we'll compute the marginal effects, goodness of fit measures such as pseudo R square, likelihood function value, and we'll also examine the fitted values. We'll compare these values for both logit and probit models. Lastly, we'll take a value of threshold value of 0.5 and compute the percentage of observations accurately classified, which is count R square measure for both the models, and compare their performance in predicting the observations correctly. With this, we'll conclude the case. Let us start with the case 5, which is smoke data case. Smoke data case. First and foremost, we'll read the smoke data. So we'll read the smoke data here. Now, as I run it, let's have a glimpse of this data. Glimpse. Let's see the variable. What are the variables? So this data contains 1196 observations. First, the smoke variable, whether a person is smoker or not. Then you have his age, his or her age, education, years of formal years of education, income, and pricing of cigarettes. So these are our data points. Let's start with the exercise. So first, we'll fit the model, logit and probit model. Let me write the formula first. So the formula that we are going to use in this formula, which is we want to model smoke as a function of age, education, income plus pricing. So these are the variables. This is a formula. So we'll run both the models. Logit. Logit model is with GLM formula. Data is smoke. And in the family of models, we'll specify we want binomial with link equal to logit. So this is our logit model. Now we'll run probit here. So let's summarize the results. So for that we'll use the summary command. So we'll summarize the results. Summary model underscore logit, and similarly we'll summarize model underscore probit, and then we'll interpret. Let's interpret the result. So let us start by interpreting the logit probit results. These are our logit results. We have age, education, and pricing variable as quite significant, and these are our probit results. Again, age, education, and pricing variable are significant. So I'll interpret one of them. I'll interpret logit. Probit can be interpreted in a similar manner. In fact, they are quite similar. Only there's a minor difference in terms of coefficient. So let's interpret the logit model. Now please note here, these coefficients reflect the logit function. Here is estimated value function is logit. So if you want to directly interpret the coefficient, they connect with the log of odds ratio because you are modeling logit. So what you can do is the way you can interpret logit in the form of percentage of odds ratio. Interpreting logit is much easier as compared to probit. Interpreting the logit function is easier. So in the form of log of odds ratio, I can say that for each year increase in formal education, there's a sort of 2.1 or 2.085% decrease in odds ratio. You can say 2.1% decrease in terms of percentage terms in odd ratio. So 2.1 percentage decrease in odds ratio for each year of increase in age. Similarly, for each year in terms of formal education year increase, there's almost a 10% decline in odds ratio, 10 percentage point declines. So 10 percentage decline. Pricing, we can say for each unit increase in pricing, the tendency to smoke in terms of its percentage in odds ratio, the odds ratio decreases by 2.2%. So this is how you can interpret the results for logit model, but we need to examine the marginal effect to make more solid statements. So we can also examine the marginal effect, which will give us a proper idea of the relationship, marginal effects. So the way to do it is the approach can be as follows. We can apply margins command or margin summary rather. So margin summary for logit. Margin summary gives us the average effect also, which along with their interval and their significance. So we'll examine the margin summary for logit and probit both. Significance would not change, it will remain same as we already got. So we can compare the results. We can see in terms of p-value, age, education, and pricing. Three values, as we saw earlier also, age, education, and pricing significant. And if you look at the marginal effect, they are almost similar. So we can interpret the result in a similar manner again. For example, we can say for each for each year increase in age, the probability to smoke decreases by almost 0.5%. Similarly, for each year increase in education, propensity to smoke decreases by 2.06, 2.07%. Again, for each unit increase in price, propensity to smoke decreases by 0.5%. So this is how we interpret the result. In the next video, we'll examine the goodness of fit measures such as log likelihood, pseudo R square, and count R square, and we'll also compare the ability of logit and probit models to accurately classify the observations. In this video, we'll continue with our examination of smoke data, logit probit models. We'll compare the goodness of fit measures, Then we'll examine the fitted probabilities and also compare the performance of logic probit models. So let's start with goodness of fit match, for which we have this PR2 function. And in this PR2 function, we'll supply our model underscore logit. Then we'll keep running the code. So model underscore logit and model underscore probit. Let's compare the performances. So in terms of goodness of fit, we can see the R square values are quite close. Pseudo R square around 3% and log likelihood values around 47. So it's very similar. In these kind of exercises, what is more important is the significance of these variables. So these are generally values like McFadden's R square and so on. They are important when you are comparing two models. For example, I want to know whether age variable should also go as a square and cube or nonlinear term. So then in that case, you can, the form and shape of the variable you can compare with these measures. But if you want to know the importance, significance of the variable, these results are more important, where we saw that with p-value, we saw that age, education and pricing was important. Now with goodness of fit, you can compare. For example, I can compare the goodness of fit of probit logic probit model. These are the numbers. They're generally as a comparison benchmark they can be used. If we want to examine the fitted probabilities, we'll examine the summary of model underscore logit dollar fitted values, and we'll also compare for the probit model. If you compare these probabilities, you can see the probabilities are quite similar, range from 0.13 to 0.69. So they are very similar. The distribution of probabilities are very similar. In the last step, we'll assume a threshold value, threshold of 0.5, and compare the model performances. So for this, and in fact, I'll borrow the codes. I'll not rewrite the codes. The codes are already written, so I'll rather borrow from here. So I'll specify the tau equal to 0.5. So first, the logit probit. So counts. So here I need to correct my data. I should have corrected data, which is smoke data. And in the smoke data, the variable needs to change smoke. So now things should be in order, 22%. So in fact, we have correctly classified 730 observations out of the total. Oh, sorry, has to be smoke. Now it's better. So out of the total 1100 observations, we have correctly classified approximately 730. So my 61% is the accuracy. Similarly, here I need to change the values to smoke. So I've reused the same code with minor modifications. So at tau equal to 0.5, we can see the accuracy. Both models are almost giving me exactly the same accuracy. So that means there's not much difference. And in fact, the values are also same. Again, probably the distribution of the data is same. So we are getting similar results, similar kind of results. So here also we are able to classify 730, and here also we are able to classify 730 observations. So that is about the performance of these models, count R square. So with this, we conclude the case. In this final sixth case study, it is a multinomial logic case study on education data. In this case 6, first we'll read the education data. The data has following attributes. First, the choice of education or undergraduation. 1 with no undergrad, 2 if 3-year undergrad, and 3 if 4-year undergrad. Next variable is grades, x2, overall grades normalized on a 13-point scale. Then you have family income x3, gross family income in lakhs, family size of the family members, parents' education is 1 if any of the parent has advanced education like master's, doctorate, gender axis is 1 if female, 0 otherwise, language if 1 if Hindi speaking, 0 otherwise. We'll read the data in R and conduct the following exercise and analysis. We'll run a multinomial logic model examining the relationship between the choice of education as dependent variable and independent variables x1, x2, x3, x5, and so on, as we described earlier. We'll summarize and interpret the result. We'll conduct the statistical test of significance. We'll examine the fitted probabilities. We'll also do some prediction exercises to see the goodness of fit of the data. With this, we conclude the exercise. Let's start with the sixth part of our case, part 6, on education data with multinomial logic. In this case, we'll first load the data, education data. So we'll load the data. For reference, let me copy paste the command. For reference, I'll just copy paste the command. Let us have a glimpse of data. So we have all the useful variables. We have 1,000 observations in which undergrad, board, grades, family income, family size, parents, education, gender, language, as we have described the variables already. So all the variables are here. Let's start with the exercise. So first let's define the formula. So formula is, we'll run the regression of undergrad on board plus grades plus family income plus family size plus parents education, a lot of variables in this particular model, plus gender plus language. So these are our variables. Now we'll put the model. It's a multinomial model, so we'll use multinomial. We'll put the formula and then we'll put the data education. So here, okay, so let's interpret the results now. We have executed the model. We'll use the summary command to execute this model and then summarize. So we can see the intercepts. We can see, so basically we can see the intercept, standard error, and so on. So first what we'll do is, let's see the significant variables. So how do we do that? We'll calculate the Z values. That's easy. So let's store the model. Let's store the output here. Output. Now Z equal to, so we'll calculate the Z value. How do we calculate it? So Z equal to output dollar, sorry. So we will use the coefficients. So we have the coefficients here. We'll divide these coefficients with the standard error. So this will give us our Z values. So let's see what are Z. So these are the Z values for both the models. See, the one becomes our reference category. So no, the choice of no undergrad becomes our reference category here. And now this is a two-tail testing. Two-tail test. So for two-tail test, I want to calculate p-value. That's simple. I'll compute 1 minus p norm, and I'll use the absolute Z values, so that absolute Z values, and then 0, 1, so 0, 1, and we'll multiply it by 2. So that is our p value, because these are two-tail tests, so we need to multiply it by 2. Once we get that value, yep. So let's see. So let's see what variables are significant for us. So we can see, given the p values, we can see the board. Okay, so board variable is significant, and we'll print the Z also parallelly, so we get that clarity. So we can see board value is very significant, grade significant, we can say family income is significant, family size is not significant, education kind of significant, gender is not significant, language is so. We'll, for time being, we'll remove the gender variable, we'll remove language also, although it's significant for the second case, but for now let's remove it. So language, gender, and family size, language, gender, family size. So these three variables we'll remove and we'll run the model again. So let's copy paste our model. Let's run the revised model with good variables. So we want to have board, yes, we want to have grade variable, we want to have family income, we don't want to have this size variable for now. We want parents education variable, we don't want the gender variable. Language we may or okay, so language is like so we may or may not want to keep it. Let's for now let's keep it. Let's remove it to make the model very parsimonious. So now let's run the model output. Now if I see my Z, these are all significant variables that we are interested in that I have produced here. So I have given the Z values. Now if I print the P values, they are good. So we can go ahead with the interpretation. So let's do again a quick summary of output, which is output. So all the variables are now significant. So our focus will be on interpreting these variables. Please recall, these are not probabilities what you're getting. Now, right now, these are logics. So you can interpret that way. If you want the probabilities, there is a separate route to that. But let's interpret the output for now. So to summarize the output, first and foremost, let us let us look at the, let's say for example, let's look at grades variable. Now both of them are negative. So that means let's look at choice two, choice of taking a 3-year undergrad versus no undergrad. If you're on 13-point scale, if your grade increases by 1 unit, your choice to go ahead with the 3 undergrad decreases, or rather in a way of saying the percentage, there's a percentage decrease of 28% in odds ratio for choosing the 3 undergrad program vis-a-vis the choice one, which is no undergrad. Similarly, if we look at choice with respect to three, a 4-year undergrad program, the choice to choose 4-year undergrad program decreases by 65% with each unit increase in grades. So that is slightly surprising. What about family income? If your family income is higher, family income was in lakhs. So if your family income is higher by 1 lakh, the choice to choose program two with respect to like 3-year program with respect to no undergrad, the odds ratio increases by 0.8%. And similarly, odds ratio increases by 1.25% in favor of three vis-a-vis one if your family income increases by 1 lakh. Similarly, for parents' education, that is quite a big variable. So as you can see, if your parents have a master's degree, then your choice to go ahead with 3-year programming is more as compared to the odds increases by 53%. And in fact, odds increase by almost 105% in favor of 4-year program as against no undergrad program. Similarly, for board, slightly interesting. So suppose if you have board intermediate from state or state board or central board, so that is the variable. So if you choose central board, if you choose central board, the chances are slightly lower. So that's slightly surprising result. If you are from central board, the odds in favor of 3-year program goes down by 2 points, in fact 274%, and if for the other it is 806%. So probably there's some stressful problem with this result. It can't be that a big number. So we'll more, I think more sanitized results are grades, family income, and parents education. What if I want to, let's say, obtain the probabilities? What I'll do is before that we'll go to the goodness of fit measures. For that we can refer to this PR square value. I can supply the output, sorry, the model actually. So if I supply the model, I'll get the goodness of fit measures. For example, McFadden or pseudo-ASCA is 17% and log likelihood 360. So that is one. Second, I would also like to see the performance of this model. So first I'll check the fitted probabilities. The way to do it is output dollar fitted value. So these are the probabilities and there are 1000 observations for each of the probability. For example, let's call it probability PI. Let's suppose I want the probability for event first observation. So first row. So let's look at these. Now you can see if as per this fitted value, the first case would have been one probability. First case would have been most likely one because it has 41%. Each of these probabilities have a sum of one. So for example, if I summarize P this one, this PI for observation one, each of the probability will sum up to one. So that is good thing. So you'll get a sum of one, whatever observation is summarized. You can also predict. So for example, if you want to predict using this model and providing the education data, you can predict observations. So these are your predicted values. So these are your predicted values. It is giving you three levels, 1, 2, or 3. Let's call them predict, multi, norm. So these are our predictions. We want to compare the goodness of it, or sort of how accurate this model is. Accuracy of the model. So what I can do is to examine the accuracy of this model, I can compare this object with the actual values. So I can compare this with the actual value. What is actual values? Education dollar undergrad. So this is my actual value. Now you have trues and false. So like we were doing earlier, if I sum up all the trues are taken as one and the sum would be produced. Now all I need to do is these are correctly predicted observations. So these are the correct ones. And we have approximately 1,000 observations, I think. So if I divide it by dimension of one, dimension one, which is the number of observations, let's see how many observations we have. We have around 1,000, as I said, 1,000 observations. So our accuracy or count R square of this model would be 59.5%. So this is the count R square of the model, which is around 59.5%, which is like slightly better than a coin tossing game, not very accurate, but we get the point. We get the procedure to run a multinomial logit and extract the fitted probabilities also. So with this, we conclude the exercise. To summarize this lesson, we discussed how the logit model approach can also be applied to a multi-choice variable or multinomial variable. In this approach, out of n choices, one choice becomes the reference point, and for the other choices, the probabilities are assessed with respect to this reference point. Next, we also discussed the Tobit model or censored regression model. We noted that in some cases, if the dependent variable is not observed beyond the threshold value, the model can still be estimated using maximum likelihood estimation approach, assigning that particular threshold value to the missing dependent variable, instead of excluding such observations. Next, we implemented the home ownership case, where we employed the linear probability models. We noted that while the model is easier to implement and interpret, it is afflicted by several issues related to estimation, and fitted values are not probability consistent as they move beyond 0 to 1 range. In the next case, we use group data. We noted that if data is grouped, the logit form of model can still be estimated in a linear fashion, and one can obtain probability consistent values. In the subsequent cases, namely debit card, ATM card data, grade point average data, and smokers data, we implemented and compared the logit and probit models. We computed marginal effects, goodness of fit measures, for example, count R square, pseudo R square, and log likelihood function. We compared the results from the logit and probit models. We found that if the data is fairly symmetric, then logit probit models give similar results. Lastly, we also estimated a multinomial logit case using education data. With this, we conclude the tutorial on classification case studies.